In this video, we're going to talk about a process called denaturation. You can see the word up here on the slide. I'll underline it for you right here, denaturation. All right, so we've already talked about how proteins are molecules that have a three-dimensional shape, and their shape is what makes them able to do their job. And every protein is shaped a little differently, and their shape is specifically designed so that they can do the job correctly, like a little like a tool. So a screwdriver is shaped a certain way, and a hammer is shaped a different way because they do two different jobs, so they have two different shapes. So I'm going to use this once again as my model of a protein, and you can see that it's actually it's a chain, right? It's a polymer of amino acids. It goes through the primary, secondary, tertiary folding, and you end up with a structure that looks like this. And so in this example, we're going to assume that this is albumin, which is the protein that you find in egg whites. All right. So let's imagine that this is egg white protein and it's in your fridge. What does this molecule do in the fridge? Well, it's going to be doing this. I don't know if you can see, it's shaking just a little bit. If you remember back to when we talked about heat or temperature, heat is just a measurement of how fast molecules are moving. And so at 4 degrees C in your fridge, this thing is moving because it's not frozen solid, but it isn't moving very fast. All right. An egg white in your fridge is like a kind of straw-colored, pale-colored liquid. All right, so I'm going to take my egg out of the fridge and I'm going to sit it on my counter in my kitchen. So it's going to gradually warm up to room temperature. So here's my egg white protein at room temperature. What's it doing now? It's doing this. It's moving a little bit more because now it's at 20 degrees Celsius, the temperature of my house. And that means the molecules are vibrating a little more than they were in the fridge, but it still looks like egg white. It's the same shape, it's got the same structure. All right, next I'm going to take this protein, this egg, and I'm going to crack it into a frying pan that's on my stove, and my frying pan is really hot. My stove is red hot, my frying pan is hot. So as soon as I crack this egg and the egg white protein falls onto the hot surface of the frying pan, what's this molecule going to do? Well, it's heating up rapidly. Oh my gosh, it shook and shook and shook until it completely unraveled itself. We'll do that again. Right, here's my tertiary protein. At room temperature, it's wobbling, but it's holding itself together. But as it heats up, gradually the folds just get disrupted. And my protein has now lost its three-dimensional shape. And what does it look like? Well, when egg white is heated up in a pan, it turns from a clear liquid to a white solid. Right? It actually changed how it looks, so you can actually see the result of the change in the molecules. All the molecules unfold, and the protein turns from a see-through liquid to a white solid. Now, all right, here's my fried egg. Can you unfry an egg? No, you can't. So once this thing has unraveled like this, it cannot fold itself back up. It's been irreversibly changed. So what this process is known as when you unfold a protein, this is called denaturation. That's the word on the slide here. I want you to make sure that you realize that this is not the same as breaking down the protein, because even though it's denatured, it's no longer the right shape, the chain is still here. Look, I can pull it and the bonds aren't broken. The peptide bonds in my chain are still here. So the protein has not broken down, but it has unfolded itself and it has lost its shape. And as soon as a protein loses its shape, it loses its function, so it's not going to work anymore. So denaturation is generally not a good thing, generally in terms of protein function, because generally once the protein loses its three-dimensional shape, once it becomes unfolded, it will not function. The tool is broken. It's like melting down a hammer or a screwdriver. It loses its shape. But once again, it's not broken down because it's still a chain, but it has unfolded itself. Now, why didn't it actually break apart? Why did it just unfold? Well, if you remember back to when we talked about the tertiary structure and what kind of bonds hold this together, remember it was the bonds between the R groups, the R group interactions, and those R group interactions are occurring between the bits that stick off each bead, the R groups, and those R group interactions are things like hydrogen bonds, hydrophobic interactions, and ionic bonds, and those three are not particularly strong when water's around, and especially when this thing is shaking. So you're not actually breaking covalent bonds. And this is covalent bonds holding this together. So that's why the chain didn't come apart and all the beads didn't fall off. But I did break those weak interactions that occur between the R groups. So there's like an R group sticking off of this white bead and an R group sticking off this white bead, and they interact like this. I can break that interaction, although I can't break this. There was one interaction at the tertiary level, the disulfide bridge, that was a covalent bond. Remember the disulfide bridge that can happen between two cysteine amino acids? And those actually are harder to break by denaturation. But even if you've got a few disulfide bridges holding on, the rest of it is all going to be shaken apart. So you're going to lose your shape regardless. Denaturation can occur through some different conditions. The main one, obviously, we just talked about is heat. So high heat will denature a protein because it'll shake apart the R group interactions. But anything that interferes with R group interactions will break apart or unfold a protein. And apart from heat, things like extreme pH, like extreme acidity or extreme alkalinity or basicness will interfere with these interactions and unravel the folds. And also high concentrations of salt, because salt is made of ions, Na plus and Cl minus, and those salt ions can get in between here and cause different attractions to happen and just disrupt how the folds are and how the R group interactions are happening. So heat, extremes of pH, and salt, these are all things that can disrupt protein folding and result in denaturation. If you think about it, temperature, pH, and salt, these are all ways that we preserve food. So temperature, obviously cooking, and when you cook things, really what you're doing is you're denaturing the proteins in the food to make, sometimes that makes the proteins more palatable or more digestible. Sometimes it doesn't, but sometimes it does. But also by doing that, you're denaturing the proteins in any molds or bacteria that might be in the food that could cause it to spoil. And if those bacteria's proteins are denatured, then those bacteria can't survive, they can't reproduce, and so they can't rot or spoil the food. So that's, pasteurization is another example. When you pasteurize milk, you're heating up to high temperature, denaturing proteins, stopping bacteria from being able to survive. pH, extreme pH is like high acidity. So that's an example of pickling. When you pickle things, you put it in vinegar, which is acid, and that acid denatures proteins and makes it hard for bacteria to survive because the proteins are all messed up. And salt, well, back in the old days, we don't do this so much anymore, but back in the old days, we would use salt to preserve food, like you can salt fish and salt meat. And that's the same thing there. The salt is disrupting proteins, unfolding them, making them non-functional, making it very hard for bacteria who have their own proteins to survive because of their disrupted proteins. One last thing on this slide, it does seem to imply here, this is a little misleading, that you can unfold a protein and then you can refold it back up. Now, yes, if it's gentle denaturation, maybe. If you don't completely shake it all apart like this one, maybe the protein can refold itself like we're showing here. It's getting refolded here to get back to this shape, but that's actually quite rare. Generally, denaturation is a one-step deal and it's permanent. You can't really renature a protein, just like you can't unfry an egg.